Okay, good morning, everyone. Welcome to my presentation. It's rather practical because it's basically based on my experience with working and deploying with MPI applications and the problems I encountered. So most of MPI and distributed programs tend to crash in a pretty nasty way. So you get a lot of a huge error log, and for developers, it might be difficult to find out where the problem is. For ordinary users, it might be really impossible to figure out what's wrong. And if you want a successful application, so the error reporting and treatment must be done in a nice way for easy deployment and so on. So I got one example of my application, which is crashing in a not very nice way. So basically, it's a kind of, simulation framework that runs iteratively over thousands of iterations and so on. But at the beginning, it does some memory allocations, then data loading and so on. And during this data loading phase, there might be some error. For example, the input file cannot be found or something like that. So what then happens, usually you get this terminate message, which says that on the node number 20, there is an error called HDF5 I, which means there's not enough memory for loading the data. And basically, we'll get all this error message with standard library and so on. And at the end, the code is terminated. This would be fine if you run this with a single MPI process. But if you say 1,000 processes, you will see this error message 1,000 times. So which is very hard to debug for normal people. Yeah. So what I would rather like to see is this kind of behavior. So okay, there was some error during the data loading. For example, the workload is not perfectly balanced over the nodes. So some node need more memory. And basically, there's an error here. So the application really fails. And I just want to know what happened. And in this way, so I just would like to see an error message from a single rank, just summarizing the error in such a way that the exception was HDF5I. We can have some details about the error. It was a system error caused by rank 26 in the communicator MPI convert, and that's it. So from this information, it might be much easier for me to figure out what's wrong, where the error is located, and so on. So basically, when I was thinking about my applications and trying to solve this problem in a good way, I did some literature review and so on. And basically, what I would like to use and always use in my applications is I write them in C++. So basically, error handling is done by C++ exceptions. So basically, we've got try and catch blocks. And if there's an error, so the code goes from the try block to the catch block and then solves the exception. So in C codes, you usually test every single routine for the error code and then do something. So in C++, the error handling is decoupled from the, correct pathway. So in the MPI applications, you've got mixture of these C or C++ codes and then MPI calls. So because now C++ interface was removed from the MPI, so there are no exceptions in MPI. So if there's something wrong, you've got a few possibilities what you can do. So first of all, you can check the return calls from every single MPI call, which is tedious and make this, the code hard to read. The second option is to define this default MPI error handler, which says that all errors inside MPI are fatal and the code will just crash. And you will see exactly this kind of error message repeated 1,000 times and so on. You can also write your own error handler and then do something more clever. But anyway, what it will do is just report the error from all the ranks you have. Now the problem is typical applications are composed of MPI parts, which means communication, and just local calculation. And the problem now is if the error happens inside a single rank in the calculation part. So the error is local, and the other nodes or ranks have no idea about the problem. So the simulation or the code can deadlock. And if this is the worst situation, I would say, because the code gets stuck, consumes resources, and just basically waits until the PBS or Slurm scheduler will kill it. Yeah. So when I was looking about some solutions, so a lot of papers are about handling hardware errors. For example, the whole node crashed and how we can recover from this node crash and so on. I found only a single paper talking about how to handle MPI or errors in MPI codes and how to distribute these errors. But this paper uses a special interface to MPI. So if you want to combine your code with your custom, say, compute kernels, your MPI communication, and also use third-party libraries, you've got problem because these third-party libraries are precompiled and written in a different interface. So it's not compatible. So I was basically forced to come up with something clever. And basically, I set these 3 goals for my work. And basically, the first one is I always want to a single rank to report the error. Then I would like to ensure the application will never deadlock. So I can detect the deadlock situation and somehow kill the code if it's inevitable. And the third goal was I really need compatibility with third-party libraries that don't have any idea about my error checking. So how I did it? So basically, I've got a very minimalistic design composed of just 2 classes. The first one is a descendant of C++ standard exception class and just adds some other information about the problem that happened. So first piece of information I always want to know is the type of the error. It makes me easier to parse what happened, and these types can be customized, so you can have MPI errors, system C++ errors, say solver errors, data I/O errors, and so on. Then you always need to know the rank where the exception happened. Then you would like to know the communicator, because the applications are composed of multiple communicators, and basically what you typically do is you have a single communicator per some, say, module of your code, and so on. Then you also want to know the name of the communicator, the error code. Error code is a nice feature because you can report. So when the application crashes or terminates, you can pass the error code to the scheduler and then somehow have another level of job monitoring and basically identify the problem. Then we've got a typical error message and information about the status of the code, whether it's deadlocked at this moment or not in a deadlock state, which means it can somehow recover. So basically, this distributed exception class has all the information about the problem. So the second class is the error checker. So there are 2 possible implementations. The first one is you've got a single static class in your whole code, which means you basically protect the whole code by a single error checker. Or you can create multiple instances that protect different communicators. So in a nutshell, it works by creating a side channel. So you will always take one communicator you would like to protect and then create a side channel and communicate the error messages via this side channel. And so the most important thing for you as developers are these 2 methods. One is set success, that informs the user that everything's fine, and check if section that basically returns the error that happened inside the code. So okay, maybe let's take a look at the implementation. So let's start from the beginning. So if you want to use it in the most simplest way, you just initialize the MPI and then initialize the error checker. So for this, you need the communicator you would like to protect. In this case, it's MPI convert. That means you protect the whole application. And you need some kind of timeout. So this timeout is necessary to detect the deadlock state. Then you can enter this try block and write any combination of MPI, local calculations, third-party library calls, and so on. And then you've got a catch. That basically solves all the problems inside the application. So what I would like to mention, the try block must be concluded with the set success. So this is really important because you need to know you successfully pass some stage of the calculation, basically at the end of the try block. And you typically do this anyway, because, for example, if I go back to this slide, so what you usually do is you print out some header, you've got some initialization of the application, then you would say, okay, I'm done with this part. Then you allocate the memory, you pass this checkpoint, you're ready to proceed somewhere else. So you print out this done message, then you load the data, then you run thousands of iterations, and after, say, every 20 iterations, you would like to give some progress of your code. So you really want to know where you are. So if everything is okay, so all the ranks will meet in this set success method, and then just at the end call finalize and terminate the application. If something wrong happens, the faulty ranks will go directly to this catch block. And what's important here is, so imagine you've got okay, let's talk first about the deadlock-free state. So for example, after this barrier, there are only pure local calculations. So if there's an error here, so all the ranks will come to the catch and then just figure out what's wrong. So this catch exception routine is responsible for collecting the information about the exceptions that happen in remote ranks, and then just vote which rank would be responsible to print out the error. But there might be more difficult situations. For example, there's a problem in this full method. So one rank is out of memory and basically goes directly to the catch method, and the others will enter the barrier and will stay there forever because the rank that caused an exception here just skips the barrier. So in this case, we've got this deadlock mode detection that basically says, okay, several ranks are stuck here, and just we need to find out which from the alive ranks will be responsible to report the error. So this deadlock mode is then will tell you who will print out the error. So in case of deadlock-free situation, you have the possibility to recover. So basically, you can somehow print out the error and then do something clever to recover from the faulty situation. If the application is deadlocked, so you have no choice, you will need to terminate the application. Okay, so let's take a look about how this is implemented. So I will first talk about the deadlock-free situation. So there was no blocking call after the error happened. So if everything is okay, so all the ranks will come to this set success and find out everything is fine. So how this happened? So in case of set success, all ranks within the protected communicator will send a message saying I'm fine, which is implemented as a max int value, which is sent to this global all reduce communication. So basically, after the communication, we try to find the minimum value, and if it's max int, that means all the ranks are fine. So in that case, we just continue, and that's it. If there was something wrong, and one rank was faulty, or multiple ranks were faulty, they will skip the set success method, but will enter the same communication as the first thing in the catch exception. So basically here, and in the catch exception, they will report the error by sending its own rank. So not the max int as in the case of everything is fine, but now the rank of which is faulty. And basically this all reduce operation will then return the number of the lowest rank with the error. If you would like to know all the ranks that are faulty, you can exchange this MPI all reduce method by MPI altogether, but it doesn't matter. So, okay, we are here. So basically we've got some faulty ranks, some okay ranks, and now we need to find out. So basically from the I reduce operation, we get the name of the first faulty rank, and this faulty rank is then responsible to pack the information about the error and send it to the root rank, or to the rank who's responsible for reporting the error. If the application is not deadlocked, it's typically rank with number 0. So basically we pack all information into a single message and send it via MPI send to the root rank. A root rank will just open the message, create an instance of distributed exceptions, and throw it. All other healthy rank, in this case, have no information about the error, but that's not necessary, because what we want to achieve is just we want all the ranks that are now in the success method to throw an exception to go directly and meet the others in the caching session. So basically everybody will join and continue in the same path. Yep. Okay. So after this distributed exception, all ranks are in the caching session method, and the first rank, in this case rank number 0, will print down the error, and then it's up to you what you want to do with the code. You can recover, or you can call MPI finalize and exit the simulation. So that's one way. The other situation is a deadlock situation, which means the ranks that are healthy have entered some blocking communication like MPI barrier, and will never join the error ranks in the caching session. So what then? So the faulty ranks will enter the MPI I reduce and will be waiting for the others, but these ranks will never join them. And it's implemented in such a way that this collective communication is non-blocking. So basically I can test the outcome of this operation. If I don't get the answer within the timeout, say 10 seconds, I know something is wrong, that some ranks are deadlocked, and would need to choose a different strategy to report the errors. So if this communication reduction was not successful, then we need to find out which ranks are faulty and vote amongst them the leader who would be responsible for the error message. So this is done in a custom, say, non-blocking altogether communication. It's as simple as every faulty but alive rank will send a message to all the partner in the communicator, and then just collect the answers. So the ranks that are not responsive will be declared as deadlocked, and I will get a list of ranks that are still responding. So among these ranks, then we vote the leader, which is usually the rank with the lowest rank, and this rank will then get the information about the error, cancel all other pending communication, print out the error message, and at this point, the only thing we can do is really to call MPI abort and hope the MPI system will terminate the whole application. But still, we have a single nicely formatted error message. So something about testing. So I deployed this mechanism in 3 or 4 different applications. All of them were tested with different MPI, Intel MPI and Open MPI with up to 1,500 ranks. The testing was done on Salomon, Barbara, and Carolina at IT for Innovations in the Czech Republic, but we also tested it last month at Lumi. So we know it works also there. The code is quite complex. It uses multiple modules, so there was multiple instances of the error checker, basically protecting several parts of the system. With third-party libraries, we use a distributed version of Fast Fourier Transform, FFTW. That spawns hundreds of communicators during the calculation. And we also used a distributed version of HDF5 library for reading and writing the files. So then we tried to inject different errors in multiple nodes. Some of them were, say, application-based, like file was not found, missing data set, or this quota exceeded, or wrong rank in MPI call, or something like that. Some of them were standard C++ errors, for example, out of memory, out of bounds, numerical errors, and so on. And in all cases, the application terminated correctly, so we got just a single error message, and the application was terminated, it didn't get stuck. So at this moment, the only error we cannot somehow fix is a problem that arises inside the MPI init call. For example, the application didn't start correctly, but this can be monitored by a watchdog that checks the startup of the application. So okay, that's about it. So basically, the code is publicly available at the GitHub, so you can download it, you can use it. And what I would like to mention or say as a take-home message, that this MPI error checker has a very simple interface. It has good interoperability between your code, different versions of the MPI, and third-party libraries. It can recover from, it can correctly terminate the application even under the deadlock. But what we can't do at this moment is the deadlock recovery, because we cannot somehow terminate blocking barriers and things like this. Okay, that's all. Thank you very much.
Before asking to the audience if someone has any question, I will take the advantage that I have the microphone. So, as a former C++ developer, I found all these tools very, very, very useful. Can you quantify the amount of time that people can save using that tool? Because sometimes you can get crazy because you see an error and say, oh, what is the origin of that?
Wow, it's really hard to say. So the error checking can be as simple as you basically put all the application inside a single try-catch block. And basically, every routine will report an error using a C++ exception. And then basically, at the end, you just check, okay, there's an error, where it is, and so on. So I think it really depends on what you as a developer would like to report. So you can extend this routine exception, and you can add much more information that I have at this, say, basic version. And in that case, you can report, for example, the line of code where it happened, the module file name, and so on. And in that case, it can be really helpful. Because what you usually get, for example, if you use HDF5 library, and if you can't find a data set, so it will print out this huge log of there's something wrong inside, blah, 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 blah. And it's really difficult for you to find it.
Thank you. Any other question from the audience? So if not, let's thank again, Jiri.
Thank you.